Hello and welcome to Engineering Safari. And today we'll be talking about continuous and discrete time systems. In the previous video, which I hope all of you have watched, we spoke about continuous and discrete time signals. And today we'll be talking about systems. So, this module has very few subtopics, but the important thing is that all of the all of the subtopics are actually pretty vast, and we have to spend time on understanding each subtopic and then solving a few questions to actually be able to solve questions in the exam. So, like I said, the understanding part is important, and I'll help you with it, and we'll solve as many questions as possible. And if you have some additional time, I would request all of you to please see a few more questions just for your confidence, or else whatever we cover in this video will be more than enough for the exam. So, the basic introduction to this is what is a system? A system is a device or anything that takes in an input signal. It performs an operation on it, which we denote by t on x of t, and it gives us x of t is the input, and it gives us an output y of t. So how this signal is modified and we get a different output signal is based on how we design the system. So the three main topics in this module are system properties, convolution, and correlation. So with that said, let's start the first topic for today, that is system properties. So there are five basic properties for a system. So the questions will be regarding all five. They will give you a particular system. They'll tell you what operation the system actually performs on an input signal, and you have to classify it based on these five properties. So the first one is whether the system is a memory or a memoryless system. So a memory system is also called a dynamic system, and a memoryless system is called a static system. So what these two mean is if the if the output of the signal that you're getting after the system performs the operation is dependent only on the present value of t or n, then it's called a memoryless system. And if it depends on either the past or future values of t or n, then you can say that it's a memory or a dynamic system. So the second property is whether it's linear or non-linear. We'll be covering each property in detail and how to actually write the answer after we talk about the basics of all five properties. So a linear system is a system which satisfies superposition theorem, and a nonlinear system is one that does not satisfy this theorem. So the third one is time variant or invariant. So what this property tells us is whether the delay which you put in the input is the same as the delay that you get in the output. The fourth one is causal or non-causal. So a causal system is one which where the output depends only on present and past inputs, and a non-causal one is a type of system where the output depends on the future inputs as well. So you can say that a non-causal system is definitely a memory system, because a memory system is one where it depends on the past and future values. So a non-causal one is definitely a memory system, but you can't say anything about a causal system because it can be either memory or memoryless. So, so that is about causal and non-causal. And the last one is stable or unstable. So a stable signal is also bounded, an unstable signal is not bounded. So what happens in stable and unstable is the sum of whatever signal you have. If the sum of all amplitudes in the given signal come out to be less than infinity, then you can say it's stable. And if it comes out to be infinity, then you can say that the graph is not bounded and it's unstable. So those are the five basic properties. So now we'll see what each property means in detail. And if they ask you a question on properties in the exam, how you actually have to write and show that this actually satisfies the property, because it's a subjective exam and you cannot just write the final answer, you'll have to write all the steps. So the first one is whether it's a memory less system or a memory system. So for this, let's look at a few questions. So the first question is, let's say we have y of t is equal to a into x square of t. So like you can see here, the only value of time that the output actually depends upon is t, and t is time at the present value. So you can say that this is a memoryless or static system. Thus, now another question would be y of t. Y of t here is the output and x of t is the input signal. So ax square of t is the operation that is being performed on the input signal to give us the output signal. So let's say we have y of t is equal to 3 into x of t plus 1. So this clearly depends on the future value of t, because the present value of t is uh, the present value of time is given by t. So t plus 1 means what the time would be after 1 second. So what would the function of x be after a second from the present is what will give us the output. So since the output depends on the future value of t, we can say that it's a memory or dynamic system. So and so basically what you can notice is it doesn't matter about what is outside the bracket, as long as what is inside the function, inside the input function, if that is simply t, then it's a static system. And if there is any addition or multiplication to that, then you can say that it's a dynamic system. So it doesn't matter whether you have 2x of t or x square of t. All of these don't make a difference to our answer in this case. The only thing that matters is what is inside the bracket. So if you have anything like t square, t plus 1, uh, and so on, you can say that it depends on either a past or future value of t, due to which it becomes a dynamic system. So that is about static and dynamic. The second, the second property that we'll be talking about is linearity. Is our system linear or not? So what linearity means is, let's say you have two signals, x1 of t and x2 of t. So and you have a particular system that performs the operation t on the given signal. So let's say we are multiplying x1 of t with a, and we are multiplying x2 of t with b. These are just some variables that we are taking. It's like amplitude scaling the particular signal. So then in the first scenario, what I do is I pass x1 of t through the system and I get t of a x1 of t, and I pass the second signal to through the same system. So here I get t of b x2 of t, and then I add the outputs that you get from both of the systems. So I have t of a x1 of t plus t of b x2 of t. So this is just my LHS in the equation. So, and on the other hand, what I do is I take x1 of t, I multiply it with a, I take x2 of t and I multiply it with b. I add both the signals first, and the sum of these signals is then passed through the system, right? So first I get the sum. I get a x1 of t plus b x2 of t, and then I run it through the system. So this the t operation is actually performed on the sum of both the signals. So here my answer is t of a x1 of t plus b x2 of t. So this is the RHS. So if the LHS is equal to RHS, that is if t ax1 of t plus t of bx2 of t is equal to t whole ax1 of t plus bx2 of t, we can say that if LHS is equal to RHS, we can say that it's a linear system. If LHS is not equal to RHS, then it's a non-linear system. So to understand this better, let's look at a few questions. So the first question, let's take it to be y of n. Y of n here is the output that you get after the operation is performed, is equal to e to the power x of n. So this is a discrete time system. So let's calculate LHS and RHS separately. So what we do in LHS is we take each signal and we pass it through the system, right? So let's take x1 of n as the first signal and x2 of n as the second signal. So what I do is I take t into x1 of n and I multiply it with a as well. That gives us a into e to the power x1 of n. And similarly b into t of x2 of n. The output here is b into e to the power x2 of n. So basically what you have done here is you have passed both the individual signals x1 of n and x2 of n through the system, and what the system does is it gives you the output of e to the power whatever the function of the signal is. So when you passed x1 of n, the output will be e to the power x1 of n, and when you pass x2 of n, the output will be e to the power x2 of n, and you are just multiplying different coefficients a and b, and you're just multiplying this to show like an exam, when you're writing a subjective exam, you are taking these coefficients to show the linearity. This helps us show that LHS and RHS are not equal in a easier way, else there isn't really much significance of these coefficients. So this is, I know that what I have to do is I've passed A through the system and I've passed B through the system as well. Now I need to add the outputs of both of them. So my final answer would be T of x1 of n plus T of x2 of n is equal to A into e to the power x1 of n plus B into e to the power x2 of n. Right, so this is the LHS. Now let's calculate the RHS and see if both of them actually come out to be equal. So what I do in the RHS is I first add both the signals, right? So my first signal is AX1 of n and the second signal is BX2 of n. So I add both the signals now. So I get a very simple AX1 of n plus BX2 of n. So after I add both the signals, now I will run it into the system, right? And the operation T will be performed on the resultant sum of this. So what was what did T do? Whatever signal was inputted, whatever signal was the input, it performed an operation that is e to the power that signal, right? So here the input signal is ax1 of n plus bx2 of n. So what would t performed on this signal give us? It would be e to the power ax1 of n plus bx2 of n, right? Because whatever is the input signal is straight going to the power of e. So you know that e to the power a plus b can be written as e to the power ax1 n into e to the power bx2 n, right? So this is the RHS and this is the LHS. So like you can see in LHS, it's a into e to the power x1 of n plus b into e to the power x2 of n. And on the RHS, you have e to the power ax1 of n into e to the power bx2 of n. So clearly, LHS and RHS are not equal. So what can you say? So the system is non-linear, right? So this is about linearity. Let's see another question. So let's say you have y of n is equal to g of n into x of n. So the output is a product of two functions. So again, I'll take the input signals to be x1 of n and x2 of n. So the if I run the first signal through the system alone, the output will come out to be a g of n into x1 of n. And if I run the second signal alone through the system, I'll get b g of n into x2 of n, right? So the sum of these two will give us g of n into a x1 of n plus b x2 of n, right? So this is the LHS. Now for RHS, what I do is I add both the signals and then I perform uh, the transformation on it. So I'll simply write t of a x1 of n x1 of n plus b x2 of n, and that gives us what you basically multiply g of n with whatever the input function is. So here the input function is a x1 of n plus b x2 of n. So I write g of n into a x1 of n plus b x2 of n. So this is the RHS. So like you can see here, the LHS and RHS are equal. So we can say that LHS is equal to RHS. Therefore, it's a linear system. So that is about linearity. I hope these two questions made it clear. So the third property that we'll be talking about is uh, time variant or invariant. So what a time variant, no, actually, what a time invariant system does is whatever is the delay in input signal, delay in input, the same delay will be maintained in the output signal, right? So you can compare this to a bus that is starting, let's say it has to start from a spot at 3:30 and reach another spot at 8:30. So if the bus starts at 3:35 and it reaches the spot by 8:35, this is an example of a time invariant signal because the delay at the start was 5 minutes, and at the end too the delay was 5 minutes. So the delay that you have given in the input signal should be the delay that is in the output signal. So uh, that is and how you actually write it is that the operation performed on x of t minus t naught should be equal to y of t minus t naught. So this concept is easy to understand, but in questions, the approach is what is important. So let's see a few questions here. So if we have y of t is equal to x of 2t, right? So let's say we have introduced a delay of plus t naught in the input, right? So in x of t, what we have is x of 2t plus t naught. So what we are basically forcing this delay, right? So we do not replace t by t naught. We just add t naught to whatever is inside the bracket. However, when we are talking about y of t, right? What happens in y of t is this t we replace the entire bracket. Sorry, we replace uh, t alone with T naught. So that is like not a forced delay, but a delay that is coming naturally because of the input. So in y of t, you get 2 of t plus t naught. Let's say this is t of x of t. In this, you just have x of 2t plus t naught. But in y of t, you get x of 2 into t plus t naught. So in this case, you get x of 2t plus 2t naught. So like you can see, the delay that we gave in the input was t naught, but the delay that we're getting in the output is 2t naught. That is what that is what uh, that is what is time invariant because the delay in output is different from the delay in input. So So basically, you can say that inside the bracket, if you have any product, let's say 2t or 3t or any value n multiplied with t, it's going to be a time invariant signal. And but if you have anything like n plus t or n minus t, then the delay in the output signal will not be different from the delay in input signal because this T naught is not increasing by any factor. And similarly, another case where you will get an invariant signal is if you have, let's take y of n is equal to n into x of n, right? So here, if you take a delay of n minus, if you take a delay of n naught, t of x of n simply gives us n into x of n minus n naught. So this is the delay in input. However, when I look at y of n, every single n in the expression will get replaced by n minus n naught. So I get n minus n naught into x of n minus n naught. So again, like you can see, the delay in input is not equal to the delay in output. So this is another example of time invariant system. So what we have seen is it's invariant if inside the bracket we are multiplying it by any factor. It's invariant if there is a variable, you are multiplying the entire function with a variable like n x of n, but it's variant if we have a function which is x of t plus n. Okay, so that is about time variance. Uh, The next topic is causality. The fourth property is causality. So causality is again telling us whether the value depends on past, present, or future inputs. So we say it's causal if it depends only on present and past, and it's non-causal if it depends on the future. right? So we have a very few, we have some examples like y is equal to 3 into x of t. So like you can see inside the bracket we have only t, right? So because of that, we can say it depends only on the present values. If we have something like y is equal to 3 into x of t minus 1. So this always depends on the past values alone. So we can say that this is also causal. However, if you have y of t is equal to t plus x of t plus 1. So this part is causal because x of t, this part is causal. However, since this part depends on the future, we simply say that the entire function is non-causal, right? So that is about causality. So just this one question is important because let's say we have y of n is equal to x of n by 2. So when you look at this question, you might just conclude that it is a causal signal because it depends on only the past output. Since if you take n as 1, it depend you get 1 by 2, and since it depends on a lesser value of n, it depends on the past output. However, it's not a causal signal because if n is a negative integer, then let's say we take n as minus 1, we get x of minus 1 by 2, right? And minus 1 by 2 is a future value of minus 1. So because of that, since it's not causal for negative integers, even overall it's not causal. So it has to satisfy causality at every single point for it to be called a causal signal. So that is about causality. So stability is the last property that we'll be talking about. So stable signals are signals where the sum of the first thing actually is that for a system to be stable, for a system to be stable, the input signal actually has to be stable. So if the input signal itself is not stable, then there is no point in checking for stability. So the first criteria while you do this is that the input signal has to be stable, and if the input signal is stable and the sum of all amplitudes, let's denote it by m of x, is lesser than infinity, then it's stable. And if it's equal to infinity, then it's unstable, right? So if you have a signal that is periodic, like a sine curve, this is a bounded signal. Like you can see the sum of amplitudes, it's not going to be zero, right? The sum of amplitudes is going to be a fixed number. However, if you have a graph that is exponentially increasing, like this graph, this is an example of a non-bounded graph that is unstable because the sum of all amplitudes cannot be defined. Like you can see, the amplitude is just going on increasing with the value of time. So this is an unstable graph or an unstable signal, right? So these are the five properties. I hope all of the properties were clear. And another thing is, if you have y of t and you have the sum of few different functions, and you have to check for any property, right? Even if one of the functions does not satisfy a property, you can say that the entire function is not going to satisfy the property. Like we said for this causal signal, because a part of the function wasn't causal, the entire function is supposed to be non-causal. So that is about the system properties. So just to recap, we've learned five system properties, which are memory, that is whether it depends on past or present; linear, that is if the sum of inputs, the sum of the transform of the sum of inputs is equal to the individual transform of the inputs added up. Then we spoke about time variant or invariant, which is whether the delay in input signal is the same as the delay in output signal. Then we had causal and non-causal. Non-causal is when it depends on future inputs, and everything else is a causal system. Then we spoke about stable or unstable. If the sum of amplitudes is finite, then it's stable, and if the sum of amplitudes is infinite, then it's an unstable system. Okay, the next topic is convolution. So this is a very important topic, the most important topic. So we have a linear time invariant system, right? So we just spoke about the different properties of system. So the system that we take for convolution has to be a linear system and it has to be an invariant system. So just a second. Okay, I'm sorry. So for convolution, you need to have a linear time invariant system. So let's say there is an input signal. Let's denote it by x of n, and it's you run this input signal through a system. The system has its own function which is defined as h of n, and after convolution is performed between these two functions, that is when you get the output function denoted by y of n, right? So this h of n is called a unit impulse response. And why we call that a unit impulse response is if your input signal is a unit impulse signal, is a unit impulse function, your y of n is equal to h of n, right? So because of that, we call this the function of the system a unit impulse response. So let's talk about convolution. Like I said, the output signal is given by convolution between. Convolution is denoted by this star. It's given by convolution between your input signal and the unit step response. That is the function of the particular system. So the formula for convolution is we can write y of n is summation of k of from k is equal to minus infinity to infinity x of k and h of n minus k. So first we'll talk about convolution in discrete, and then we'll talk about convolution in continuous. Alright, so like you can see, like the whole thing will become more clearer when we do a question. But for now, like you can see, the x, the input signal remains fixed, whereas we are adding, uh, we are actually time shifting the unit impulse response, and then we are time reversing the unit step response as well, because it's minus k and plus n. And then what we do is we multiply both of these responses, and then we add the responses from minus infinity to infinity, right? So there are four operations which are being performed. The first thing is also another important thing is you can also take it as x of n minus k plus h of k. There's no difference between the two. You can fix either signal and perform the other operations on the other signal. It not plus. I'm so sorry. It's multiplied. You can fix either signal and perform the operations on the other signal. But usually, since the function for unit impulse response is a much simpler function, we tend to fix the input function and perform operations on this. So let's have a look at a question. A question would make this a lot more clearer. So let's let's take x of n. So at 0 we have 1, at 1 we have 1 by 2, and at 2 we again have 1 by 2. Like I said, we are only talking about discrete functions here. Continuous functions will be covered later on in the lecture. No, sorry, this is h of n, and x of n is from, so this is x of n, 0, 1, 2, and 3. So the value for these two is 1, and the value for these two is half. So I hope everyone's first module is clear, because the concepts of time reversal and time shifting are very important here. And I'm just going to assume that when I explain the time shifting and reversal that is happening, everyone can grasp it. So the first thing we need to find out is from what point to what point will the output signal actually exist in, right? So we have a very simple method for that. We know that h of n is defined from 0 to 2, and we know that x of n is defined from 0 to 3, right? So we simply add the lower limits, and we simply add the upper limits as well. So 0 to 5 is where our output signal will be defined. And so like you can see, 0 to 5 basically means 6 responses. Okay, so now let's start performing the convolution. So like I said, the first thing that we'll do is, let's replace this x of n and h of n and n with k, right? So let's fix our input signal. Let this be x of k, and this is k. So the input signal is fixed at this particular point. All right, 1, 1, 1 by 2, 1 by 1 and 1. All right, so the unit impulse function is where we'll perform our operations. So what we do is, the first thing that we have to do is we reverse the signal, and then we start performing shifting on it. All right. So from what you remember in the first lecture, you know that time shifting by a positive number means we shift to the left, right? So k plus t naught is usually shifted to the left. But since we have minus k here, whenever we time shift this particular function, it moves to the right. Okay, and similarly, if we are time shifting by a negative integer, it moves to the left. That is one thing to be kept in mind. So the first thing that we'll do is, we'll find h of minus k. Right. So h of minus k just means that you reverse the entire unit impulse signal. That is, you flip it about the y-axis. So you have 1, you have 1 by 2, and you have what was the question? Wait, I think I made a mistake here. This is supposed to be 1 by 4. So this is 1 by 4. Okay, so what we do is, the formula for shifting was h of n minus k. So we take values of n one by one, and we shift the signal by 1 unit each, right? So we shift it by, we first keep it in the initial position, and we add both the signals. Then we shift h of minus k by 1 unit, and then we add both the signals. And then we shift it by 2 units and add both the signals, and we go on doing that, right? So we know that our formula is y of n is equal to summation of k of k is equal to minus infinity to infinity x of k into h of n minus k, right? And we also found out that y is defined from 0 to 5. So what we do is, first we take the value of n as 0, we find y of 0, then we take n as 1, we shift it by 1, then we perform the multiplication and add all the inputs. Similarly, we find y of 0, y of 1, y of 2, all the way till y of 5. And after we find all the corresponding y values, we plot it on the graph, right? So let's say we have y of 0, that is when n is 0 here, right? So for n is equal to 0, we simply have x of k into h of minus k. So these are the true graphs that we should be multiplying. So when you multiply these two graphs, you can clearly see that there is nothing on the negative side of the input function, and there is nothing on the positive side of the unit impulse function. So the only place where both of these functions actually exist is at 0, right? So we simply multiply the functions only at 0. And at 0, you have the value of the function to be 1, right? So I usually what we would be doing is we would plot the value of the signal at each integer and then sum all of them up. So since we have only one particular signal here, the sum comes out to be 1. So next what we do is we find y of 1. So here we know that for y of 1 we need to write h of 1 minus k. So h of 1 minus k basically means we shift this by 1 unit to the right. So for y of 1, we need to find the graph of h of 1 minus k. So 1 minus k basically means at 1, my value is 1. At 0, the value is 1 by 2. And at minus 1, the value is 1 by 4. Right. So now I need to multiply this with x of k. So like you can see now there are two places where the graph is common, that is 0 and 1. So the multiplied graph, that is x of k into h of 1 minus k, looks like this. So at 0, this is 1 by 2 and this is 1. So at 0, we have the product which is 1 by 2. At 1, this is 1 and the input signal is also 1, right? So at 1, our output is 1. So now what we need to do is we need to sum up the values of all the signals, because that is what uh, is done in convolution, right? Our output signal will be the summation of all the signals that we get when we multiply these two terms. So like you can see, it's 1 by 2 plus 1, which is 3 by 2. So y of 1 is equal to 3 by 2. So the next thing that we need to do is for finding y of 2, we time shift this by 2 units. So when we shift it by 2 units, the graph that we get is something like this. So at 0, I have 1 by 4. At 1, I have 1 by 2. And at 2, I have 1 by 4. Right. So now let's multiply this with the, like you can see in all, now the values are common in 0, 1 and 2. So we have 1 into, let's draw the graph for the multiplied output. So this is x of k into h of 2 minus k. So we have 1 into 1 by 4 is 1 by 4. 1 by 2 into 1 is 1 by 2. And 1 by 4 into 1 by 2 is that what we're looking at? No, sorry, 1 by 2 into 1. Sorry, this is not 1 by 4, whatever it is. This is literally 1. Okay, so this is 1 by 2, and then we have 1 into 1 by 2, which is again 1 by 2. So I hope you all have the graph of x of k, because that is fixed. For every new value of h of n minus k, we have to multiply it with the original x of k. So in the original x of k, we had 1, 1 and 1 by 2 in these three values. So 1 by 4 into 1 has given us 1 by 4. 1 by 2 into 1 has again given 1 by 2. And 1 into 1 by 2 has given 1 by 2. Right? So now we have done multiplication. So the last step is adding up of the values in each signal. So we have 1 plus 1 by 4 plus 1 by 2 plus 1 by 2 is 5 by 4, right? So we can say that y of 2 is equal to 5 by 4. So this is the value of x of k into h of 2 minus k, that is y of 2. So now we need to repeat this for y of 3. So now what we do is we have shifted the signal by 3 units, right? So we have shifted it one more from here. So at 1 we have 1 by 4. At 2 we have 1 by 2, not 1 by 4. At 2 we have 1 by 2, and at 3 we have 1. So now we again need to multiply this with x of k, and now the common regions are 1, 2 and 3. And at 0 we'll get 0 because the h of 3 minus k graph doesn't give us a output at 0. So at 1, the value of x of k was 1, right? So 1 into 1 by 4 gives us 1 by 4. At 2, the value of x of k was 1 by 2. So 1 by 2 into 1 by 2 again gives us 1 by 4. And at 3, the value of x of k was 1 by 2. So 1 by 2 into 1 gives us 1 by 2. So this is the value of x of k into h of 3 minus k. Now again we need to add all of the three signals, which is we have 1 by 4 plus 1 by 4 plus 1 by 2. So this gives us 1, right? So y of 3 is 1. So now we have two more operations to go. So for y of 4, the h of k graph would be shifted by 4 units, right? So this has one more shift now. So at 2 we have 1 by 4, at 3 we have 1 by 2, and at 4 we have 1, right? So now we need to multiply this with the value of x of k. The value of x of k at 2 was, now see, at 0 and 1, the resultant graph 2 will have no values. The resultant graph will be defined only from 2 to 4, right? So sorry, not even 2 to 4, just 2 to 3, because x of k was defined from 0 to 3, and after that it did not have any signals. So at 0 we have no signal, at 1 we have no signal, at 2 we have 1 by 4 into the value of x of k at 2, which was 1. So at 2 we have 1 by 4, at 3 we have at 3 we have no at 2 the value of x of k was 1 by 2 as well. So at 2 we get 1 by 4 into 1 by 2, which is 1 by 8. At 3 we have 1 by 2 into the value of x of k, which was 1 by 2 again. So here we have 1 by 4. 1 by 4. So now adding up of these two signals, we get 1 by 8 plus 1 by 4, which is 3 by 8, right? So this is 3 by 8. So finally we have y of 5, which is then this has been shifted by one more unit. So at 3 we have this is 1, 2 and at 3 we have the value of h of 5 minus k, to be 1 by 4. At 4, the value is 1 by 2. And at 5, the value is 1. Right? However, we know that x of k is not defined in 4 and 5. So we just have to look at the output that we're getting at 3. Right? So what was the value of x of k at 3? That was 1 by 2, right? So for 0, 1, 2, we have no values. And for 4 and 5, 2, we have no values. And for 3, we have 1 by 4 into 1 by 2, which is giving us 1 by 8. And the sum of this comes out to be 1 by 8 itself because that is the only signal. So y of pi is 1 by 8. So the final answer would be this is y of n and this is n. So we need to find out y of 0, right? Y of 0 was 1, y of 1 was 3 by 2, y of 2 was 5 by 4, y of 3 was 1, y of 4 was 3 by 8, and y of 5 was 1 by 8. So these are the values that we need to plot on this particular graph. So at y is equal to 0, we have 1. At y is equal to 1, we have 3 by 2. At y is equal to 2, we have 5 by 4. 3 by 2, 5 by 4. And at y is equal to 3, we have 1 again. At y is equal to 4, we have 3 by 8. And at y is equal to 5, we have 1 by 8. And for all other values, it's simply 0. Right? So this is how we perform convolution when it's a finite and discrete function. So just to make sure that everything was clear here, what we do is we fix the value of x of k, right? This will not move. And on the other hand, this x of minus k, it keeps shifting. So to find y of 0, we put n as 0 in this. So we multiply these two graphs and sum up all of the individual responses. Then what we do is we keep x of k fixed. We shift h of minus k by 1 unit. So h of 1 minus k. And again we multiply h of 1 minus k with x of k. And the new product that we get here, we again sum up the responses. So for y of 2, we time shift h of minus k by 2 units and again multiply it with x of k and then sum up all the responses. So by doing that, we get the value of y of n for all values of n from 0 to 5, and then we plot each of the values on the graph for the corresponding n value, right? So this is 1, this is 3 by 8, and this is 1 by 8. So this is how convolution is done. So I hope that was clear for everyone. Okay, so let us, there are a few properties of convolution which can make convolution somewhat easier, which is x of n convolution of del of n is equal to x of n itself, and x of n convolution of del of n minus n naught gives us x of n naught. Uh, no, x of n minus n naught. Okay, so these are two properties which we can use to make convolution easier. Okay, but these properties can only be used if your input signal has I shouldn't say it can only be used. I would say it's only suggested to use them if the input signal has very few values for which it's defined. So for example, in this previous question, the input signal was defined at 4 different points. So in that case, the following method is not suggested. If your input signal has only one or two inputs, then we can use this method that I'm going to tell you. Okay, so wait, let me take a question where we have less inputs. So we have h of n here, and we have n here. At -1 we have 1, at 0 we have 3, at 1 we have 2, and at 2 we have -1, and at 3 we have 1. 0, 1, 2, and 3. Okay, and x of n is given by 2 here and -1 here. Okay, so this method for convolution can be helpful when we are using only two of when we have very few inputs. So we can write h of n as in terms of the unit impulse function, and we can write x of n2 in terms of unit impulse function. So see, if your unit impulse function is shifted one step to the left, what do we write it as? That is equal to delta of n plus 1, right? And when the unit impulse function is exactly at 0, but it has a higher amplitude, we can simply amplitude scale the unit step function, right? So this is at 0 and its amplitude scaled by a factor of 3. And as you go to the right, it means you're shifting it by a factor of -1. So this will be 2 del of n minus 1. So the next one is amplitude scaled by a factor of -1. So we have minus del of n minus 2 plus del of n minus 3. Okay, this is h of n in terms of unit impulse function. So x of n would simply be 2 del n plus no minus del of n minus 1, right? So now what we do is we perform convolution between these two functions, which gives us the output x of n convolution of h of n. So let's write, since x of n has very few terms here, let's just write x of n as 2 del n minus del of n minus 1, and the convolution operator is performed on h of n. So this can be written as 2 delta of n convolution with h of n minus delta of n minus 1 convolution with h of n, right? So for the properties that we had x of n into h of n into delta of n gives us x of n itself, right? So here we can say that the output for this is simply 2 h of n, and the output for this is going to be h of n minus 1, right? So, so this is our output. So now let's have a look at the actual responses of h. I'm sorry, just give me a minute. I'll be back. Okay, I'm very sorry. I'm here. I'm sorry for the constant disturbances today, but this time is not a very convenient time. So, anyway, I'll just go through the question again. So, wait, h of what we were trying to do is we are trying to represent both our input function as well as the unit impulse function in terms of the delta function alone, right? So if we have the delta function at -1, it's denoted by delta of n plus 1. That is, the delta function has been shifted one step, one unit to the left. And here we have delta of n, but it's amplitude scaled by a factor of 3. Similarly, we have shifted the delta function and amplitude scaled it, and we've gotten the expression for h of n. And similarly, for x of n2, we did the same thing, and we got x of n as 2 delta of n minus delta of n minus 1. So this has been amplitude. Uh, that is, yeah, this has been amplitude scaled by a factor of -1. Right. So we know that the output y of n is actually given by convolution of x of n and h of n. Right. That is what our output actually is. It's the convolution of the input signal and h of n. And that is how we got the output for the first and second signals, right? So see, since we can actually keep x of n constant and expand h of n2 in terms of the unit impulse function, but since x of n has lesser terms, I am choosing to write x of n as this. So see, the convolution operator is very similar to a multiplication operator. If you have a minus b into c, you can write this as ca minus cb, right? So that is exactly what I'm doing here. I'm applying convolution with respect to h of n alone, and then I'm applying convolution with the second term. I'm sorry, again, there's a disturbance. I'm sorry, I don't know why there's attendance for. This is the third time they're coming for attendance. Hello, is the audio clear now? Okay, I think the audio switch, the mic switched off due to the size of the call. At least that is what Google Meet had to say. Okay, let me just share again. Okay, so anyway, continuing, like I said, if you have a minus b into c, we can write it as a into c minus c into b, which is exactly what we've done here. We have applied convolution of delta n with h of n and minus delta of n minus 1 with h of n, right? So by we just learned the properties of convolution, right? Convolution of any function with delta function gives us the same function again. And yeah, convolution of any function with delta function shifted by n naught units gives us the value of that function also shifted by n naught units, right? So here we can see h of n with two del. Let's ignore the two here. Del of n convolution of h of n should give us the same function, that is h of n. And similarly, h of n convolution, the convolution of h of n with a shifted delta function. It's shifted by 1 unit, right? So even the h function would be shifted by 1 unit. So we have to write h of n minus 1. So that is the convolution applied. Now, how do I actually draw the graph for this? Is let me just put it up. Wait. Right. So I have to find the graph of 2 of h of n and h of n minus 1. So like you can see, this is the graph of h of n, right? So 2 into h of n basically means this graph will be amplitude scaled by a factor of 2. So if I have to write that, let me draw the graph here. So this is 2 into h of n. So at 0, what are the values here? 1, 3, 2, and 1. 2, minus 1, and 1. So I will multiply each value by 2, right? So at minus 1, I had 1. So now I will get 2. At 0, I had 3, and now it's 6. At 1, I had 2. That will be 4. At 2, I had minus 1, which will be minus 2. And at 3, the value of h of n was 1. So after amplitude scaling, the value will be 2, right? So this is 2h of n. So now let's plot the graph for, let me just go to the next page. So let's plot the graph for h of n minus 1. So what happens here is the entire graph is shifted towards the right by 1 unit because you are time shifting it by plus 1, right? So let's just perform the time shifting and see what we're getting. So we have at minus 1 we had 1, so that comes at 0, and at 0 we had 3, that is shifted to 1. So at 1 we have 3, at 1 we had 2, so now that is shifted to 2, and so on. So now at 3 we have minus 1, and at 4 we have 1, right? So now let us subtract this, right? Let's subtract the let's subtract h of n minus 1 from 2h of n. So what we do for that is we subtract each value. So at minus 1, 2h of n is 2 and h of n minus 1 is 0, right? So this is the final value of y of n, because I know that y of n will be the difference between these two graphs. So let us try to solve that. So yeah, so at minus 1 it will be 2 minus 0, which will just be 2. At 0 this graph is 6, and h of n minus 1 is 1. So we are left with 5. Okay, so this is 5 at 0. At 1 we have 4 and here we have 3. So the difference is going to be 1. And at 2 we have minus 2 here, and here we have 2. So the graph will be minus 4. At 3 we have at 3 we have 2 here, and we have 1 here. So the graph, uh, wait, what do we have here? 2, and we have minus 1 here. So 2 minus of minus 1 becomes 3. So at 3 the value is 3, and at 4 we have 0 here and we have 1 here. So this is minus 1, right? So this is the final graph of y of n, right? So just to go through what we did again, we represented both x of n and h of n in terms of delta functions, and then we uh, applied convolution to each delta function part individually, and then we used our delta function properties, these two properties, and we simplified it. We got two graphs, which is 2h of n and h of n minus 1, and then we found the difference between these two graphs, and that is what gave us the output. So why I said this can be used only for, this is preferred to be used only for small or fewer values of x of n is because, let's say there were 4 or 5 values of x of n. What you would have to do is you would have to apply convolution to each function and then use the delta function properties, and you would have to find the difference between 5 graphs. I mean, at the point of this, these properties were to simplify the question, so that wouldn't serve any purpose because we can just use the initial method instead. So when you have fewer values of x of n, you can use this property, and for more values of x of n, you can use this method. So I hope that is clear. So that is about discrete time convolution when it's finite, right? So now let's take an example of infinite signal convolution. So here let's take x of n is equal to u of n, and h of n is equal to u of n minus 3, right? So like u of n means it's the value is 1 at all integral values all the way to infinity, and u of n minus 3 means the unit step function has been shifted 3 units to the right. All right, so this is 1, 2, and 3. Here the value is 0 for h of n, and from here onwards we have 1, 1, and so on all the way till infinity, right? So now again, the initial few steps for convolution remain the same, right? We fix x of n, so like we take x of k here and k, and then we reverse the unit impulse graph. We take h. Okay, yeah. So we were talking about infinitely long signals and convolution between two infinitely long signals. So we had the input signal as unit step function and the unit impulse function, which is the function of the system as uh, unit step function shifted to the right by 3 units, which is u of n minus 3, right? So while applying convolution, like always, we are keeping the input signal fixed, and we are going to reverse the unit impulse function by we we are going to reverse the unit impulse function, and from 3 onwards we will have 1, right, all the way to minus infinity. Okay, so now what we need to do is we'll have to take different values of 1 like we did initially, right? So the first thing that we have to calculate is y of 0. That is, what is the value when you multiply x of k and h of minus k without any shifting. Here, the value is n minus k, right? So, because we are calculating for y at 0, it will simply be h of minus k. So at this point, like you can see, there is no common value between h of minus k and x of k. So the multiplication of these two will simply give us 0. Now for y of 1, what we do is we shift this 1 unit to the right, and it still remains 0 because there is still no common region. For y of 2, it remains 0 as well. But when we get to y of 3, that is h of 3 minus k, it has been shifted by 3 units. So now at 0, we have the common value that is equal to 1. So y of 3 is equal to 1 at 0 alone, right? So now when I shift it by 4 units, I have the value of 1 from 0 to 1. Similarly, for y of 5, I have 1 from 0 to 2. For y of 6, it's again 1 from 0 to 3. Right? So basically, I can simplify this as y of n is equal to 1 from 0 to n minus 3. However, this is true only for uh, y that is greater than 3. For y that is, sorry, for n, this function is only for n greater uh, n greater than or equal to 3, right? Because for n lesser than 3, the value of the output function was always 0. So I can write it as y of n is equal to summation of k is equal to 0 to n minus 3 and 1, right? Because basically I'm adding up ones. Let's take the example of y of 4. I'm adding 1, the value of 1 at 0 and 1 at 1, right? So that is 2. So similarly, if I have y of n, I will be adding I will be adding 1 from 0, 1 from 1, and so on till uh, n minus 3. The value of the graph remains 1 at n minus 3. So I will add 1 these many times, right? So the formula of summation of 1 from 0 to a particular number gives us the upper limit plus 1, right? Because I have added up 1 n minus 3 times, but I also have 1 at 0. So my final answer is n minus 2, right? So my y of n is defined as, let me write it here, y of n is defined as 0 for n is lesser than 3, and it's defined as n minus 2 for n is greater than or equal to 3. I hope it's fine now. I hope this question is clear. So let's take another example. Okay, wait. I heard that this question was not clear. So wait. So see here, since the limits are not defined, we have to approach it a little differently. All right. So see, our input function is the unit step function. So from zero, all the 0, 1, 2, 3, all the way till infinity, the value at each point will be 1, right? And h of n, that is the unit impulse function, is unit step function shifted to the right by 3 units. So from 3 all the way till infinity, the unit step function has values of 1 at every single integer, right? So what we do for convolution, x of n, convolution of h of n, is we have to time reverse h of n, and then we have to multiply it for different values of n, and then sum up all the values at that particular instant, right? So the first step is time reversal. So after doing that, let's take different values of n. So we start with n is equal to 0, right? So y of 0 will be summation of x is equal to minus infinity to infinity. So time reversal is done because that is the first step in convolution, right? The formula for convolution is x of k and h of n minus k. So the first thing that we do is time reversal, and then we time shift it by units by different values of n. So we have done time reversal first, and then we are shifting it one by one. So for n is equal to 0, we shift it by 0 units. That is, we take the exact same graph and then we multiply it with x of k. So like you can see here, there is no common region between these two. So for n is equal to 0, multiplication of these two graphs will give us 0, right? So y of 0 will be 0. And similarly, even if you shift it to the right by 1, and then even by 2 units, there is no common region between h of minus k and x of k, right? So even h of 2 minus k, the graph would be at minus 1 we have 1, and then so on we have 1 till infinity. But there is no common region between x of k and h of 2 minus k, right? So because of that, even at y of 2 we have 0. However, when we get to y of 3, that is h of 3 minus k, this h of minus k is shifted to the right by 3 units, right? So 1, 2 and 3 units. So at 0 we have 1 now. So now we have a common region between x of k and h of minus k, right? So now that we have a common region, when we multiply these two, we'll get a graph which has only 1 at the origin and 0 everywhere else, right? So the value of y of 3 is 1 at 0 alone, right? So now when I time shift it by 2 units, I'll have 1 at 0 and 1 at 1. Those are the two common regions, right? So that will become 1 from 0 to 1. So when I shift it by a few more units, the the common region between these two graphs, right? The x of k and h of minus k keeps increasing. Like I'm shifting it towards the left. So the common region between these two goes on increasing as I shift this more and sorry, I'm shifting it towards the right. So the more and more I shift it towards the right, the more and more I get a common region in between. Right. So like you can see for y of 3, at y of 3, I have 1 only at 0. At y of 4, I have 1 at 0 and 1. At y of 5, I have 1 at 0, 1 and 2. Similarly, it keeps on going. So like you can see, the value stays from, so the value goes from 0 till n minus 3, right? So I can say that the value is varying from 0 to n minus 3, whenever n is greater than 3. For n is lesser than 3, the value of y is simply 0. Okay, like you can see, because there is no common region in the graphs between these two. So because of that, we define that part separately, and we define the part for n is greater than 0 separately, right? So what we have to do is, there were four steps for convolution. The first step is reversal, which we did, and then we shifted, and then we shifted, then we multiplied. Now the last step is we have to perform addition, right? To perform to find y of 3, I have to add all the values in the graph which are present, right? So at y of 3, what is my graph? At y of 3, the graph is I have a 1 at 1, sorry, a 1 at 0 alone. So adding up all the values in this graph, I simply get 1. And at 4, I have 1 at 0 and 1 at 1. So the sum of all values is 2, right? So similarly, we have to, but since it's going on till infinity, right? Because we have to find a generalized expression for y of n. So for that we can write the sum goes from k is equal to 0 till n minus 3 times. Right? We have to add 1 those many times, because this is the one I got from 0, this is the one I got from 1, this is the one I got from 2, and so on. And I get ones all the way till n minus 3. Right? So the formula for summation is, when you are adding up uh, I mean, the formula for summation of ones is, when you are performing the summation from 0 to a particular integer, let's say 0 to n, 1, we get n plus 1, right? So since we are adding it from 0 to n minus 3 here, we get n minus 2, right? So that is the generalized expression for y of n. So if I have to find y of 3, right, I simply, why is this board so, okay, I'll just write it here. If I have to find y of 3, the formula will be n minus 2, which is 3 minus 2, and that is 1. So like you can see from the graph, we are getting 1. So this is the generalized expression without actually drawing each graph and then adding up the values. So now I can define y of n as 0 when n is lesser than 3, and n minus 2 as n minus 2 when n is greater than or equal to 3. Okay, so this is the final function of y of n. So that is how convolution is performed when you are adding. Convolution is performed when you have an infinite series. All right. So I hope that was clear. So now that we're done with discrete, let's talk about continuous series. All right. So in continuous series, we obviously won't have a summation. We'll have integration over a particular region. And here the output will be given as convolution of x of t along with h of t, and this will be given as integration minus infinity to infinity x of tau into h t minus tau dt, right? So here the tau is basically similar to the k that we had in discrete, and t, the small t is similar to the n that we had. All right. So let's take a question and see how it's solved. So if anyone has any doubts, they can just put it on the group or through any common friends, because I'm saying. So the question is, x of t is equal to e to the power minus at into u of t, and h of t is equal to u of t. Alright, so what this u of t multiplying e to the power minus at into u of t does is it tells us that we are only going to be looking at the positive side of the graph. Anything on the left side of the y-axis uh, will be ignored. All right. So this is x of t, and since it's exponential, it's a negative power of an exponent. It's a constantly decreasing curve. Right. So this is how x of t looks like, and it goes all the way to infinity. And h of t again is unit step function, so it remains 1 till infinity. Right. So again, the first few steps of convolution remain the same. So the first few steps of convolution remain the same. That is, you keep x of t constant. You write in that instead of x of n, we used to write x of k. Nothing is positive. I said since the exponential power is negative, it will be a constantly decreasing curve. So yeah, like I was saying, in discrete we replace x of n with x of k. So similarly, instead of x of t, we write x of tau and h of tau. So yeah, so we fix the value of x of tau. We perform reversal on the unit impulse function, and then we go on time shifting, right? So the first operation that we'll do is reversal on h of tau. So h of minus tau, and we get unit step function, but in the other direction, all the way to minus infinity, right? So this is the value of x of tau, and this is the value of h of minus tau. Now let's see at y of 0. Y of 0 basically means no shifting, right? So here we have the value only at 0, right? So we have the value present, tau is present at 0. Let's write it as this. Tau is present at 0. So next what we do is let's shift this by 1 unit. So upon shifting it by 1 unit, you will get the value from tau is present from 0 to 1. Okay, so here what happens is it's not at 0 and 1 alone. It's a continuous graph. So because of that, it will exist at every single point from 0 to 1, like 0 0.1, 0 0.2, etc. So that is for 1, and for 2, tau will be present from 0 to 2, and so on. So similarly, you go on writing this till tau. Let's take t itself. So for that, tau will be present from 0 to t. All right. So this is for positive values of n. Okay. What if we take a negative value of n, and we shift this towards the left? All right. If we take y of minus 1, there will be no common region because this graph has been shifted away from the origin, and the x of tau graph is starting from the origin itself. So for anything, let's say y of minus 1, y of minus 2, and everything, for all of these the value is 0 because shifting to the left means that there is no common region, so you end up getting 0. So the only thing that we'll be calculating is for t is greater than or equal to 0, what am I doing? I am going to integrate it from 0 to t, right? Because at y of 1, tau is present from 0 to 1, and at y of t, tau is present from 0 to t. So what I can write as y of t is equal to integration of 0 to t, and my function is e to the power minus a tau uh, into into h of t minus tau, right? So h is just unit step function, so we can ignore it here. And we have d tau here. So upon integrating this, we get e to the power minus a tau by a from 0 to t, and that gives us 1 minus e to the power minus at divided by a. Okay, so this is y of t. So y of t is defined as in two regions. So whenever t is lesser than 0, I get 0, and whenever t is greater than or equal to 0, I get 1 minus e to the power minus at by a. Okay, so that is how you perform convolution for continuous time signals. It's almost the same thing. It's just that you have to integrate it instead of just summing up the values. So let's just solve one more question here. Let's take x of t is equal to e to the power minus 3t into u of t minus u of t minus 3. So this is the last question for convolution, and correlation is almost the same, and in fact it's a easier version of convolution. So we are almost done with all the major concepts. So let's take h of t is e to the power minus t into u of t. See, anytime you are multiplying, you are given any function as a product of u of t. It means you just draw this function and take only the side to the right of the y-axis. If you are given any function and it's given as a product of u of minus t, it means you just take the function which is on the left of the y-axis, that is the negative part. Alright, so let's start solving it. So what is important to notice here is that u of t minus u of t minus 3. What does this actually come out to? See, u of t is from 0 all the way till infinity, we have 1. And u of t minus 3 is from 3 all the way to infinity, we have 1, right? So upon subtracting these two, the part after 3, right, it gets removed because you have subtracted this part out. So the only thing that is left is from 0 to 3, you have the value as 1, and after 3, the value is simply 0, right? So the function is defined only from 0 to 3, and what you are doing is you are multiplying e to the power minus 3t into 1 only in this region, because after that it's 0, but in this region it's 1. So I can write the graph for x of t as something like this. So it goes from 0 till 3, and after that it's just 0, right? So this is the curve for x of t, which I will write as x of tau, right? And the graph for h of minus tau will be unit step function, but in the sorry, it's not unit step function, it's e to the power minus t. Wait, let me just write the graph for h of tau first. So h of tau, the graph will look something like this all the way to infinity. So the graph for h of minus tau will be the exact reversal of this. It will go towards the left all the way to minus infinity. Okay, so now this is the graph for x of tau, and this is the graph for h of minus tau. So the first step in convolution is done, which is reversal. So the next step is we'll start multiplying for each value of t, right? So y of 0, let's see what the common region is. The common region here is simply 0, right? And another thing is y of minus 1, y of minus 2, and all of the negative values of t, we are going to get 0 because right now the only common region between h of minus tau and x of tau is 0. So if we shift this towards the left more, we are just going to get no common regions, which is 0, right? But at y is equal to 0, we have a common region only at 0, right? So the value of tau is present at 0 only. At y of 1, the value of tau is present from 0 to 1. At y of 2, it's present from 0 to 2. Alright, and at y of 3, the value of tau will be present from 0 to 3. Okay, but this is where this pattern stops, because after 3, the graph of x of tau is simply 0, right? So regardless of how much you shift your unit impulse function to the right, the common region will simply always remain between 0 and 3. So after y of 3, whatever you take, the value of tau will always remain 0 to 3, because that is the only common region. After that, you are not going to have any common region. Okay, so the only place where you have to make more specific observations is when t is between 2 and 3, right? So here, let me write it on the next page. So between 0 and 3, sorry, not 2 and 3. So in this region, I have y of 2 is equal to 0 to t. Like you can see, y of 1 will be 0 to 1, y of t will be 0 to, y of 2 will be 0 to 2, y of 3 will be 0 to 3, and so on. And also in continuous, you don't have to take only integral values. Even if you take y of 2.5, tau will exist from 0 to 2.5, right? So y of t anywhere between 0 and 3 is given by integration of 0 to t e to the power minus 3 tau into what is h of t here. Here the unit impulse function is not just step function, so because of that you can't really, what do you say, you can't really ignore h. So you have to write the value of h here, which is e of minus t plus tau d tau. So after that, so see, we are differentiating it with respect to d tau, right? So e to the power minus t can be taken out because that is not the variable we are looking for. It will simply be a constant, and then we'll integrate this e to the power minus 3 tau uh, plus, no wait, this will be minus whatever, I've written that by mistake, sorry. This will become plus tau d tau. So I have e to the power minus t 0 to t e to the power minus 2 tau d tau. Alright, I hope everyone is understanding. So upon integrating this, my e to the power minus t remains outside, and inside this I get 1 minus e to the power 2t e to the power 2t divided by 2. Okay, so this is the value of the function between 0 and 3. Alright, between 0 and 3, the value of tau is defined between 0 and t. That is whatever the value of the function you are trying to find. Okay, and at t lesser than 0, we already mentioned that it will be 0. So we won't be talking about that. But let's see, for t is greater than equal to 3, uh, y of t will just be 0 to 3 e to the power minus 3 tau e to the power minus t minus tau dt. Okay, so the only thing that is different is the limits here, because the limits will always be defined from 0 to 3 only and not to whatever value of t you're taking. So regardless of what value of t you take above 3, the answer will come out to be the same. I mean, the limits of the answer will come out to always be the same. So you can the integration is similar to the previous one, just that the limits will be different. So I hope you can integrate that. So that is we get y of t as a piecewise defined function. That is for t lesser than 0, you're going to get 0. For t between 0 and 3, you get a different value. And for t greater than 3, you get a different value. And that value is based on whatever integration we just got. Okay, so that is about convolution. I hope everything was clear. And if it's not, you can send the doubts through WhatsApp, and I'll see what can be done to clarify it. So the last topic is correlation, and this is a very easy topic in comparison with convolution. But the thing is, it's also very similar to convolution in the sense that the operations that you're performing remain almost the same. You take two functions, you take a input function, the unit impulse function, and then you perform certain operations on it. The only difference between correlation and convolution is that what we did in convolution was we the first thing we did was time reversal, and then we after time reversal we after time reversal we after time reversal we shifted the graph, and then we multiplied it with the fixed input signal graph, and then we took a sum of all the inputs which are present, right? The only thing that will be missing in correlation is the reversal. So x of x of t and h of t both remain fixed. The only operation that will perform on h of t is the time shifting. There is no reversal. Okay, so you shift it by each unit and then multiply, and then you take a sum of all the inputs. So just give me a second. I'll get this material. Yes. So yeah, the form correlation is of two types. Okay, the first type is called autocorrelation, and the second type is called cross correlation. Okay, so autocorrelation is when x of t and h of t are the same, and cross correlation is when they are not the same function. So the only another important point about correlation is uh, while talking about convolution, I mentioned that x of n and convolution of h of n can be written as h of n convolution of x of n, right? However, while we are talking about correlation, let's denote correlation. Let's denote correlation with r. Let's say r x x. Okay, we are talking about autocorrelation. So where both x of t and h of t are the same. Okay, so let's denote this as r x of x is equal to integration of minus infinity to infinity x of t into x of t minus tau dt. Right. So here there is no reversal. You are just shifting x of t by tau units, and then you are going on multiplying, and then you just go on multiplying. If you have r x y, then you have minus infinity. This is cross correlation. You have minus infinity to infinity x of t y of t minus tau dt, right? So this the second graph, which is h of t, right? That gets shifted by tau units. So what I was saying is that like x of n convolution with h of n was equal to h of n convolution with x of n, but the same doesn't apply to correlation because here r of xy is not equal to r of yx. R of xy is actually equal to minus r of yx. Okay, so if you are taking, so this r of xy that we got will be equal to minus integration of minus infinity to infinity x of t minus tau y of t dt. Okay, so that is about correlation, the different properties in correlation. So I hope that was clear. And for complex signals, uh, these properties that we just spoke about are are applicable only for some real signals. For complex signals, we have a few different formulae where we just apply conjugate in most of them. So for complex signals, Rxx will be equal to minus infinity to infinity x of t and complex conjugate of x of t minus tau dt. Okay, and similarly, if you have r of x h, that will be given by integration of minus infinity to infinity x of t, and here it will be h conjugate of t minus tau dt. Okay, so for complex numbers, the what do you say? The second term, the term which is getting shifted is taken as a conjugate and not taken directly. So let's just solve one question for correlation. So let's say x of t is equal to e to the power minus at into u of t. Okay, and they have asked us to perform autocorrelation. Right, so see, since we are familiar with convolution, correlation is it's almost no big deal because what we do is we fix x of t, and x of t is, this is the graph of x of t, which is given as e to the power minus at, and the other graph, which is x of t, x of t minus tau is given as t, is given here. And what we do is this graph is the same, and it's just shifted by it shifted to the right slowly. Okay, so like you can see at the start, what is the common region? At t is equal to 0, from 0 to infinity, everything is common, right? Because it's literally the same graph. You have in autocorrelation, the graph x of t and h of t are both the same. So at the start, before you actually shift the graph, like I mentioned, there is no reversal in correlation, right? We just start shifting. So here, both the graphs are literally the same. So at t is equal to 0, the graph is defined from 0 to infinity. Okay, not t, sorry. This is tau, right? Tau is the shift in the second graph. So for tau is equal to 1, the graph is there between 1 to infinity, because this graph has been shifted 1 unit, right? So there is between 0 and 1, there is nothing in the second graph. So any multiplication in that region will give us 0 itself. So tau is equal to 1 is defined from 1 to infinity, and tau is equal to 2 is defined from 2 to infinity, and so on. So this is defined as tau is equal to n will be defined from n to infinity. So the main aim here is that we should generalize, right? So for uh, for t greater than 0, I can write the formula as t tau is defined from n, sorry, not n, this is continuous we are talking about, so t. So for t is greater than 0, tau is defined for t to infinity. Okay, I hope it's clear. So what we do is, let's find the correlation Rxx is equal to integration of 0 to infinity e to the power minus at into e to the power minus a of t minus tau dt. Okay, so again, see, since we are differentiating with respect to t now, the tau part comes out. So I have e to the power a tau integration of 0 to infinity e to the power minus 2at dt, right? So integration of when I go on integrating this, I get e to the power 8 tau that remains outside, and this will be e to the power minus 2at divided by minus 2a, and it will be the limits that we'll put are 0 and infinity. So then we get e a tau into upon putting infinity we get 0, and upon putting 0 we get 1 divided by minus 2a. This minus and minus cancel, so we get e to the power a tau divided by 2a, right? This, the 2 isn't cancelled, the minus is cancelled. Alright, so this is the value of Rxx when t is greater than 0. Right. Now let's check the value for t is lesser than 0. So see, like you can see, at 0 the graphs are literally the same, and as you go on shifting to the left, right? See, this is a graph that stretches all the way to infinity, and this is also a graph that stretches all the way to infinity. So now let's say I move it a little to the left. I move this graph to minus 1, right? This graph will be defined from minus 1 to infinity, and this graph will be defined from 0 to infinity. So when I multiply these two, the graph will the output graph will still be defined from 0 to infinity. Regardless of how much I shift this to the left, it will, since it's an infinite graph, it will be defined from 0 to infinity always, and this graph is always defined from 0 to infinity since we are not shifting it anywhere. So the product of 0 to infinity and, let's say, n to infinity will always give us 0 to infinity. So whenever t is lesser than 0, tau is always defined from 0 to infinity, right? So wait, I think I did a mistake here. This integration of 0 to infinity was actually for t lesser than 0. I'm very sorry. The thing is, the graph is defined from 0 to infinity for t is lesser than 0. So whenever we integrated the function from 0 to infinity, this was performed for t is lesser than 0, and for t is greater than 0, like we actually found the limits to be t to infinity, right? So for t is greater than 0, we'll actually integrate it from tau to infinity, and we have e to the power minus at minus e to the power minus a t minus tau, and this is dt. So upon integrating this, I actually get e to the power minus 8 tau divided by 2a, and this is for t is greater than equal to 0. I'm sorry for the confusion. Like you can see, for t is greater than 0, the function is defined from t to infinity, and for t is lesser than 0, the function is only defined from 0 to infinity. So based on what the function is actually defined from, like in whatever region the function is defined in, that is the region where that those are the limits that we are supposed to take. Anyway, the function inside doesn't change. The only thing that changes depending on the type of shifting that you're doing is the limits. So finally we get y of t is equal to e to the power minus 8 tau divided by 2a. For t is greater than equal to 0. And for t is lesser than equal to 0, I have e to the power a tau divided by 2a, right? Yeah, by 2a. This is for t is lesser than 0. So I hope that was clear. And with that, we've come to an end of correlation and the end of the whole chapter. So if that is, I hope you all understood the concept and